Welcome to Cambridge IGCSE Physics, Lesson 15.1, Particle Forces and Properties. Today we explore how forces between particles determine the properties of matter. Let's examine our learning objectives for today. By the end of this lesson, you will be able to know forces and distances between particles affect properties. This means understanding how attraction and repulsion between particles determines material behaviour. Understand particles include atoms, molecules, ions, electrons. These are the fundamental building blocks of all matter. Relate particle behaviour to properties of solids, liquids, and gases. This connects microscopic particle interactions to macroscopic observable properties. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, particle forces, which means attractive or repulsive interactions between particles. These include van der Waals forces, ionic bonds, and covalent bonds. Second, intermolecular distance, which means the space between neighbouring particles. This distance varies with temperature and pressure. Third, material properties, which means observable characteristics like density, strength, and conductivity. Understanding these terms precisely is crucial for mastering particle physics. Let's explore our first core concept, particle forces. The fundamental principle states that forces between particles determine material properties. This means the strength of attraction or repulsion between atoms and molecules controls whether a substance is solid, liquid, or gas. In solids, particles experience strong forces and remain close together in fixed positions. In liquids, moderate forces allow particles to move but stay relatively close. In gases, weak forces mean particles move freely with large distances between them. The key relationship is that force strength is inversely proportional to distance squared, following Coulomb's law for charged particles. Now we examine the experimental method for investigating particle behaviour. This follows Cambridge IGCSE standards. The apparatus needed includes a thermometer for measuring temperature, a controlled heat source like a Bunsen burner, ice as the starting material, water for the liquid phase, and a beaker to contain the sample. The method consists of these steps. First, place ice in the beaker and record initial temperature. Second, apply gentle heat and record temperature every minute. Third, observe and record state changes at melting and boiling points. Safety is paramount. The hazards include hot surfaces that can cause burns, steam that can scald, and glass apparatus that can break. Therefore, you must wear safety goggles, use heat-resistant gloves, and ensure good ventilation. Let's work through our first example. The problem states, calculate the density of a substance given particle spacing data. We are given particle mass equals 2.5 times 10 to the power minus 26 kilograms, and particles per unit volume equals 3.0 times 10 to the power 28 per cubic meter. We need to find the density of the substance. Step 1. Write the equation. We use the density formula, which is Rho equals n times m, where Rho is density, n is number density, and m is particle mass. Step 2. Substitute the values. We write RHO equals 3.0 times 10 to the 28 per cubic meter, multiplied by 2.5 times 10 to the minus 26 kilograms. Step 3. Calculate. Multiplying these values gives 750 kilograms per cubic meter. Step 4. State the answer. The result is 750 kilograms per cubic meter to three significant figures. Example 2 applies particle theory to real data. The problem is, analyse how particle spacing changes with temperature using experimental measurements. The data shows temperature in Kelvin versus average particle separation in nanometers. Now we analyse. First, plot the data points. Looking at the graph, we see a clear linear relationship between temperature and particle spacing. Second, identify the pattern. As temperature increases, particle spacing increases proportionally. Third, calculate the gradient. The slope is approximately 0.002 nanometers per Kelvin, indicating thermal expansion. Fourth, interpret the result. This means higher temperature provides more kinetic energy to particles, overcoming intermolecular forces and increasing average separation. The linear relationship confirms the kinetic theory of matter. Mathematical skills are crucial in particle physics. Let's examine three key skills. First, force-distance relationships. For charged particles, we use Coulomb's law. F equals K times Q, 1 times Q2, divided by R squared, where K is Coulomb's constant, Q1 and Q2 are the charges, and R is the separation distance. For neutral particles, van der Waals forces follow F, proportional to 1 over R, to the 7th power. Second, kinetic energy calculations. The average kinetic energy of particles equals 3/2 times Kb times T, where Kb is the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin, and T is absolute temperature. Third, density from particle data. Density equals n times m divided by v, where n is the number of particles, m is particle mass, and v is volume. Now practice what you've learned with these three questions. Question 1 is basic level. It asks, a solid has particles separated by 0.3 nanometers. Calculate the number of particles in 1 cubic centimeter. This tests your understanding of particle spacing and number density calculations. Question 2 is intermediate. It states, explain why gases have lower density than solids using particle theory. This requires you to apply particle concepts to explain macroscopic properties. Question 3 is advanced. The question is, a substance changes from solid to liquid at 273 Kelvin. Describe the particle behavior changes during this phase transition. This tests your analytical understanding of particle dynamics. For all questions, remember to show you're working clearly, include units in every step, and check your answers make physical sense. Physics principles power our modern world. Let's see how today's concepts apply in practice. In materials science, engineers design stronger alloys by controlling how particles arrange themselves. Understanding particle forces helps create materials with specific properties like strength, flexibility, or conductivity. In pharmaceuticals, drug delivery systems use particle size control. Smaller particles dissolve faster, while larger particles provide sustained release. The particle forces determine how drugs interact with body tissues. In nanotechnology, scientists manipulate individual atoms using particle forces. This creates electronic devices like computer processors and solar cells. These applications show why particle physics matters. Career-wise, materials engineering designs new substances, pharmaceutical research develops better medicines, and the semiconductor industry creates computer technology. The concepts you learn today become tomorrow's innovations. Let's review the solutions. For question 1, the answer is calculated as follows. First, find the volume per particle by cubing the separation distance. 0.3 nanometers cubed equals 2.7 times 10 to the minus 29 cubic meters. Then divide the total volume by volume per particle. 1 cubic centimeter, which is 10 to the minus 6 cubic meters, divided by 2.7 times 10 to the minus 29 cubic meters equals 3.7 times 10 to the 22 particles. For question 2, gases have larger particle spacing due to weaker intermolecular forces, resulting in lower particle density compared to solids where particles are tightly packed. For question 3, at the melting point, particles gain sufficient kinetic energy to overcome some intermolecular forces, transitioning from fixed positions in the solid to a mobile arrangement in the liquid phase. Now, exam success tips. Always show you're working for partial credit. Include units in every calculation step. Check if answers are reasonable. Unrealistic values indicate errors. Read questions carefully, identifying command words that tell you what type of response is required. Let's summarize today's lesson. The key points to remember are: first, particle forces determine the state of matter through attraction strength. Strong forces create solids with fixed particle positions, moderate forces allow liquid flow, and weak forces enable gas expansion. This fundamental principle explains why substances exist in different phases. Second, the distance force relationship shows that closer particles experience stronger forces. This inverse relationship follows physical laws like Coulomb's law for charged particles and van der Waals interactions for neutral molecules. Third, material properties result from collective particle behavior. Macroscopic characteristics like density, strength, and conductivity emerge from microscopic particle interactions. For further study, review the different types of particle forces and practice-related calculations. Work through additional density and kinetic energy problems to build confidence. The next lesson covers kinetic theory of gases, which builds on today's work by exploring how particle motion creates gas pressure and temperature relationships.